For the weekend, should have completed 63 to 96 in the review for Chapter 10. Remember, our Chapter 10 test is scheduled for the next class day. We got some time for questions right now if anybody has anything after you finished up those assignments over the weekend. Anybody interested in asking about any stuffs? Oh, Lily. 88. Okay. Oh, yes. So 88 says r is equal to 2 cosine, 6 theta. And we should have x, y, and 60-degree point symmetries. So I think that the only one that's going to be tricky is the y. Did you get the other two to work out, Lily? Oh, the y was the one that I think you have to be sneaky on. Yeah. Do you want it? We can do the other two, but if you just care about the y, let's just do the y. That's fine? Okay. So for the y-axis symmetry, we would do negative r, or I'm sorry, let's write it this way. Replace negative r, or r theta with negative r negative theta, right? The problem is that if we do that, and we try to go ahead and do this, and you use your odd-even identity, you're stuck with an extra negative sign that you're not supposed to have. So the trick that we're going to use here is I'm going to use the definition of a negative radius on a polar coordinate, and basically then just flip that across. So I'm going to make the r positive and then add pi to the angle measure, because that's still the same polar coordinate, right? And now I'm going to do this way. And that's pretty sneaky. So I distribute the 6 through. And then I do my difference of two angles formula for cosines. It's going to be cosine 6 pi times cosine 6 theta. And then it's plus, just put the 2 there, sine 6 theta, or 6 pi sine 6 theta. Now, cosine 6 pi is the same thing as cosine of 0, which is just 1. And sine of 6 pi is the same thing as sine of 0, which is 0. So that stuff just drops off, and I'm left with the same thing I started with. So this was the trick here, is you just had to convert the form of the polar coordinate. And that was pretty sneaky, Mr. Kula, because you didn't do an example like that in the notes. And I'm like, well, you caught me. But that's why we take questions on all this stuff, is when we run into something that we're not sure about or can't figure out, maybe there's some trick we hadn't thought of. And that was the case here. Cool? Josie.
On the review packet, can you please do question 3 part C?
Sure. Review question 3, part C. Okay, so to have done this, we would have had to write our parametric equation for part A. I'm going to copy that in real quick. And obviously, if you didn't have this part correct, little hope that we're going to be able to do parts B and C correct. But I'm assuming that you got part B with what you're asking. Okay. So there's my parametric equation. Let's draw a picture kind of what we're looking for. So we have the ball here at like 3 feet. And we're trying to figure out where we can put it so that the ball still just skates over the top of that 10-foot fence, right? Does that make sense, Josie? So what we're looking for is what x coordinate when the ball's height is 10, right? So remember when we solve a parametric equation, we're taking a t and mapping it to an xy. And since these xy's only depend on t, if I have one of them, I can use that to solve for t and then plug the t back into the other equation to get the missing coordinate. So what I'm going to do is I'm going to take 10 and set it equal to the y equation. And solve that for t. So to solve this, I need it to be equal to 0. So I'll subtract 10 from both sides. And this is a quadratic equation now, so I'm just going to apply the quadratic formula. And then we'll just type that into our calculator to solve. There's going to be 2 answers here. I'm just going to want the bigger value because clearly, like, if that's 10, you know, there's going to be like, well, I guess that's probably at the vertex. But anyways, maybe that's fine. Maybe it's fine. So let's do this. First, I'm going to make sure my calculator is in degree mode, which it wasn't. Woo! Glad I checked. All right, so I have negative 82 times sine 39 plus or minus. I'll do both of them here. I'll start with the plus. 82 sine 39. Notice I'm putting that whole thing in parentheses and then squaring it. Got to make sure you do that if you do the sine 39, 82 sine 39 squared without that extra set of parentheses around it. It'll only square the sine 39, and that's not what we want it to do. So get the rest of those guys in there. So I get 0.142-ish. And then my other one will be when I subtract. Remember, I can't do the plus or minus on my calculator, so I just have to do them as 2 separate pieces. And 308.3 would be the other one. So this is definitely the one that I want, right? So what I'm going to do then, since that's the t value that gives me this coordinate, I can take that t and plug it into my x of t equation to figure out the x coordinate at that spot. So remember again that these parametric functions, the t is like a lurking variable. That's the input. And the output is both x and y. And because x and y are independent of each other, they're just defined on t. They're not defined on each other. if I know either the x or y coordinate, I can find the t and then use that to find the other coordinate, the one that I'm looking for. So that'd be 196.49. Does that feel okay, Josie?
Yes.
Is that a little bit clear as to kind of what's going on, the interplay between the equations and what the t really does? Yeah. So again, these are all, like, once you get it, they're pretty simple because all you're really doing is like solving a quadratic equation or something and plugging it back in. But like if you don't understand what's going on in the relationship between x, y, and t, you read it and you're just like, oh, what is he? So the picture, I think, is helpful because it kind of outlines, do you know x or y, right? Whichever one you know, you're going to use that corresponding equation to solve for t. And once you have that answer for t, you can plug it back into the one you're looking for, in the equation you're looking for to get the other part. And it's really the same thing for any of these kinds of parametric story problems. They're all kind of the same like that, which is nice because it's like, oh, okay. Like the details of the solving might change, but like the process is still the same. Yeah, of course. I talk too much sometimes. I think you were done with me 5 minutes ago, but that's okay. Good. That's what we're shooting for, right? Okay. Who's next? Eddie.
Can we go back in the problem set, like on the earlier question?
Yeah, what's up?
Can you do one of the parallelization of the line through the column? Can you do 31?
Yeah, man. All right, so 31. Okay, so it's the parameterization for a line through these points. This is pretty easy if you do it, well, even regardless of kind of how you do it. My suggestion would be to use the vector equation for a line to do this. So remember, R0 is a point vector, so you could use either one, either point as your point vector. And V is your direction vector. To find that, all you're doing is the head minus tail rule. And it doesn't matter which one you make your head and which one you make your tail. I usually just make the first one the head and the second one the tail. So that's -6, 9. And since this is, we can make our, then, I don't know, call this R of t then. Our parametric equation. So I have 10 plus -6t, or just 10 minus 6t for x. And then 3 plus 9t for y. And since this is a line, it's going on forever, so I can just use all real numbers as my parameter. If it was a line segment, that's a little bit different, but this one says it's just a line, so.
You actually do a line segment?
Well, if this is a segment, the only difference here is that this would be -1 to 0 or 0 to 1. So it's just a guess and check. So if I plug -1 in for t, I would get 16 and then -6, right? Which is my other point. So if it was a segment, that would be the interval that I would need. But as long as you make your equation as using the vector line equation, finding the interval for the parameter is always going to be either -1, 0, 0, or 0, 1. Yeah, John. Yeah, man. So here we're just wanting to convert from rectangular to polar. Okay. So our equation that we're given is this. And going from rectangular to polar, really we're just going to be using...
Oh wait, I copied it down. I put the wrong constant value. Right.
Oh, okay.
And I was left with the number, but
No problem.
Thank you.
Yeah, no problem. That's always that's a Mr. Kulik mistake right there. If you wrote down 71 or something, you're just like, what the heck?
3, and I was like left with 3.
Oh, you just read it from 82.
Yeah.
Ah, I hate it when that happens. Okay. Anybody else before we get moving here? Alrighty. Now, as we mentioned earlier, today we're just going to be starting chapter 15, or not 15, 11, or 15 in some other class I teach. Now, chapter 11 is a pretty short chapter. In fact, it's one I could do in a day if I wanted to, but I don't really want to, and I don't think you guys probably want me to, considering we're taking a test next class period. If we finished all of chapter 11 in a day, we'd be taking another test like 3 classes from now, and that seems like nobody really wants that. It'll still be quick, though. I think there's only 3 sections in this chapter. They're all pretty easy. To a great extent, we're just rehashing things we talked about in Algebra 2, maybe with a little bit more depth. And maybe like one idea extension, but for the most part, these are fairly easy set of topics. All right. So section 11.1 is about the complex plane. So let's do a little recall from last year. So we have the imaginary number I. What's I equal to? Square root of -1. Great. And that would imply then also I squared is -1. So we took that imaginary number along with the real numbers, and we formed a new set of numbers called the complex numbers. The symbol we use for that set is like the C with the bar in it. And those complex numbers are of the form A plus BI, where A, B are real numbers, and I is that imaginary number. So this A part we call the real part, and the BI piece we call the imaginary part. So if we were back working with the real numbers, and I asked you to order these numbers from least to greatest, and we had like, I don't know, 0.83, 5/6, 10/13, 7/9, and like the square root of 3/5 or something. I don't know, just making up a couple of some numbers here. And I want you to order them from least to greatest. How would you do that? Should be a fairly trivial problem for students at your level. Lily? Convert them all to decimals, and then once they're decimals, it's easy to see which one's bigger than the next one, right? Okay, let's do that. The easiest way to convert these to decimals, since they're all numeric, is with our calculator. Obviously, I don't have to do anything with 0.83. So 5/6, just a little bit bigger than that one. 10/13, okay, that's the smallest one so far. 7/9 is the next smallest one. And then 3/5 is in between those two. Okay, so we'd have 10/13, square root 3/5, 7/9, 0.83 and then 5/6 or something, right? Everybody's okay with that? And because these things all have an order from least to greatest, we can place them on a number line, right? Now that we've identified their decimal, it'd be no problem placing them on a number line. Everybody's cool? Okay. And that's pretty trivial, right? What if we had asked you to do the same question, but had given you complex numbers? What are you going to do with this? You can't really convert them to decimals, right? And that's out of the off the table. Is there anything we can do with this? No, man. There's no ordering. So we can't order these from like smallest to biggest. And as a result, like inequalities don't make sense when you're talking about two complex numbers. There is no greater than, less thans for complex numbers, which is fine, whatever. But what it also means is that we can't place complex numbers on a number line. And if you remember, this was like kind of fundamentally how we define addition and subtraction and stuff. It was basically like counting things on a number line. So what are we going to do then? Well, it turns out we need a two-dimensional way of placing these numbers. That two-dimensional system is called the complex plane. So the horizontal axis we call the real axis. The vertical axis we call the imaginary axis. So like here's a labeled complex plane. So if I wanted to plot on the complex plane 4 plus 3i, I would count 4 over on the real axis and 3 up on the imaginary axis. And there's 4 plus 3i. And let's say maybe we have -2 plus I. To plot this one, I'm just going to go 2 to the left on the real axis and 1 up on the imaginary axis. And there's, -2 plus I. Everybody feel okay with that idea? Now, okay, Mr. Kulig, this seems pretty easy. This basically is the same thing as doing what? Plotting points, right? Like, okay, there's like an X and a Y coordinate. Whoop-de-dee-doo! Why are we bothering with this? Well, I hinted at earlier, if you remember going back to like, elementary school, to do something like 3 plus 5, or 3 plus 2, You found 3 on the number line, and then you went 2 spaces over, and then that was like your answer, right? You guys remember kind of doing this way back at the very beginning of elementary school? This is why we need the number line, and this is why we're going to need the complex plane. Because to define like the addition of these two numbers, I'm going to start by going to 4 plus 3i, and then I'll go like 2 units over and 1 unit up. And that would be the result, which would be 2 plus 4i. So what do we end up doing really here? Yeah, just add the real parts together and added the complex, or the imaginary parts together. Oh, well that's really nice. So in general, if I want to do either addition or subtraction of 2 complex numbers, we're just going to combine the real parts together and then the imaginary parts together, and it's like that easy. You know what I mean? Let's do a concrete example here for a moment just to make sure we all got it. Sound good to you guys? Okay. All right, so let's say we got a couple of real numbers. So let's say I have 3 complex numbers, z1, z2, and z3, and I want to evaluate 4 times z1 minus 2 times z2 plus 1.5 times z3. Well, this is basically as easy as you think it is. So we're just going to substitute our values in. Then we'll take the real pieces and add those together, and then or combine those together, and then the imaginary pieces and combine those together. And ta-da! This is pretty easy, right? It looks a lot like what you do in like an Algebra 1 class with X's there instead of I's. Doesn't it? Yeah, no big deal, right? Also worth pointing out to you that your calculator can handle a problem like this if you make sure your calculator's in the complex number mode. So your mode should be A plus BI. You could do the same thing here. The I button you get, or the I you get by pressing second and the decimal point. And then you can just type this in just like it looks like on your sheet of paper. And calculator gives you the same thing, right? No big deal. Everybody feel good so far? No big deal, right? Pretty easy. All right. So the number line, way back in elementary school, allowed us to define addition and subtraction, right? The other thing that the number line can be used for is another definition. So let's say you have some, I'll use a different letter, some real number k. How do we define the absolute value of that real number k? So go back to your algebra, pre-algebra here and think about what the definition for an absolute value is. Hint, it had to do with the number line. Yeah, so it's the distance from k to 0 on the number line. So for example, if I had the absolute value of 2, or negative 2, excuse me. So here's negative 2, 2 units away from 0. So the absolute value of negative 2 is 2. Does that ring a bell? Again, we're going back to like pre-algebra kind of topic, but that's okay. What if we wanted to do then, let's say we have some complex number. What's the absolute value of a complex number have to be? So a distance from that complex number to what on the what? Great. So the origin on the complex plane. Now, just for clarification purposes here, the origin on the complex plane is still the number 0, right? It represents 0 plus 0i, which is still just 0. So you could say 0 there instead of origin. That's okay also. So let's think about that for a moment then. So we have some complex plane here. Let's say that we have this complex number a plus bi. So this distance here is my absolute value of that complex number, right? So how could I compute that? How could I compute that distance? Oh, guys. No ideas? We said this was just like plotting points, right? So we could just use the distance formula. Yeah, that's an excellent idea. It's the natural thing to do, or somebody I think was starting to say the Pythagorean theorem. Yup, you could think about it that way too. But this is the point. So does the absolute value of a complex number have anything to do with dumping negative signs? Nope. But it's a simple calculation. Oh man, this looks kind of familiar though. Doesn't this look familiar? Like, think back to last chapter. What does this kind of look like? You know, in the polar coordinate system, r squared was x squared plus y squared, right? So guess what? Sometimes we call this absolute value of z. We also sometimes call it r. What? Mr. Kulik. And when we talk about the absolute value of a complex number, oftentimes we'll refer to it as the modulus. The modulus is just a fancy mathematical term or a more general mathematical term for the distance or the length of something. So in most cases, when you look at the distance between two things, that shortest path is a straight line. Is it always that case? No, man. When's an example of when it might not be that case? When you're not operating in the Cartesian plane, specifically on a curved surface. Do you know any curved surfaces you move around on? The Earth is curved. So if you are traveling a short distance from like here to the corner in the room, the curvature doesn't really matter because it's a big stinking planet and the curve is pretty slight on that kind of a scale. But if you're traveling from like, you know, New York to Beijing, the shortest path there is actually like, you know, it's like it's curved or whatever. It's not quite the same. So like the distance calculation to go from New York to Beijing is not just like, oh, it's like grid these things out, make it a coordinate system, distance form in. Nope, doesn't work like that because of the curved surface. So like there's a lot of different distance functions you might have to use, and the modulus is just a generic term. So like we don't have to spell out like, oh, is this curved distance or flat distance or some other kind of weird distance? Like maybe you're talking about how far it takes to go from like one corner in the city to another corner. Again, can't take a straight line because there's like, the streets don't go in a straight line. You'd have to like, you know, go around the blocks or whatever. Like that's another distance function you might have to define. It might be useful. So just like sometimes just straight lines aren't possible. Anyways, modulus is just a generic name for like a distance function. Yes?
So how come we try writing blue there instead of the I? Why couldn't you take out the I?
Because if you thought about it as a coordinate system, like A plus BI is really just the point AB, right? That's why we dropped the I. Good point. I kind of skated past that. I wrote it down and I said it, but I was probably talking fast. Because I just get excited sometimes. I like these foundational things. You're like, what? Why? I like all these little connections between the stuff you did in elementary school and the stuff you're doing in like, you know, an upper level high school class. It's like, oh, this is really the same thing. All this stuff that I did way back then still matters. It's like still the same foundation. It's like, yeah, man. And ideally, if you have good teachers, they like kind of preload that at even the elementary or middle school level and like are using the definitions, and because they are the same definitions we use later on. And it's really nice that it's all building on itself. You know what I mean, guys? And if you didn't remember, you didn't have, you know, like the greatest instruction at that level. That's why we're redoing it now in such a way. But you're going to get excited about it. Okay. So we have that, right? And so we have this distance that we can use to describe, or that we can describe the distance that a complex number is from the origin. If we're doing that, though, we could also define like the standard position angle that complex number is from the origin. What do you think this is related to? Boy, that looks familiar, doesn't it? How many times has that particular little guy come up here, that tangent of theta is equal to y over x? I don't know, about 4 or 5 times, maybe more so far this year. Woo! This angle oftentimes we'll refer to as the argument. So we have the argument and we have the modulus. Taken together, those can describe the position of a complex number inside the complex plane, correct? Just like we could use the polar coordinate system to describe the location of a point inside the inside the Cartesian coordinate system, right? So guess what? We're going to define now another way to represent a complex number. So that complex form, or that trigonometric form for complex number is just z equals r times cosine theta plus I sine theta. Why does that work? Well, A is really r sine theta, and B is, let me make sure I wanted to put that, whether I put that in there or not. Just r sine theta. Right? Which is exactly the same definitions that we had from the polar coordinate system, right? X was r cosine theta and y was r sine theta. Woo! Mr. Kulik, is this any different than all the stuff we were just doing in the last chapter? Not really, man. Just some different names. That's nice. I like it. I like it when we start the new chapter and it's the same thing that we did in the last chapter. It's like, why are these 2 separate chapters? You don't even need to do that. And it's like, well, this is why I think second semesters may be a little bit easier, is because there's so much like repetition. It's like, oh yeah, this is the same thing we did. Oh yeah, they do this the same way we did this thing. And just like the skills pop up over and over and over again, which is cool, right? It's cool. All right, let's do a quick example. So let's say we want to write -2 plus 5i in the trigonometric form. So I need 2 things. I need the modulus, which is just going to be -2, or the square root of -2 squared plus 5 squared, or the square root of 29. And then I'm going to need the argument. To get the argument, I'm going to plot -2, 5. We're looking for this angle theta. So this is my reference angle alpha. And this is pi. Let's add to the directions that my theta should be between 0 and pi, just so we're going to do it in radians. Been a minute since we did stuff in radians. Most last chapter we were in degrees a lot of the time. Come back and do a radian version here. So theta then is going to be pi minus alpha, where alpha is the tan inverse of the absolute value of b over a. So when I type that into my calculator, you get about 1.95. Mr. Kulik, how'd you do that without actually pulling your calculator out? I've done this problem 4 times now. I just remembered what it was. I can't actually do tan inverse of 5 over 2 in my head and then subtract it from pi. Okay. So if we put this all together, then I have z equals r times cosine theta plus I sine theta. Dun, 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 dun. Okay, yeah.
So when you find the argument and b over a, what if a is 0?
What if a is 0? Then you're on a quadrant, and you can just know it's going to be, well, it's going to be like, 0, 90, 180, 270, 360, depending on which quadrant it's lying on. So if either the real part or the imaginary part is 0, then you're just on a quadrant, and you don't even have to, like it just kind of, oh, it's right there for me. I don't even need the inverse. Does that make sense? So yeah, good question though, right? Because again, if -2 was 0 instead, you can't actually type in your calculator tan inverse of 5 over 0. Calculator's gonna go, not gonna do it. But it's an easy problem to solve just by looking at the picture. You know what I mean? All right. What if we want to go the other way? Let's say we want to write, I don't know, 5 cosine, 3 pi over 4 plus I sine 3 pi over 4. In standard form, and again, when we say standard form, I just mean a plus bi. Well, we'll just start by distributing that root 5 through. And cosine 3 pi over 4, well, you could type that in your calculator, making sure you're in radian mode. Or maybe you recognize that as a unit circle angle. I do. What's the cosine of 3 pi over 4? Anybody remember? Too slow. It's root 2 over 2. Or sorry, negative root 2 over 2. Sine 3 pi over 4. Who remembers that? Too slow. It's positive root 2 over 2. Should have been a giveaway after I told you what the cosine of it was. Remember, fourths are the multiples of 45, and all the 45-degree multiples are the same for sine and cosine. I didn't give you enough time. You had it. Well, next time you'll get it, I'm sure. So when I multiply that together, I get negative root 10 over 2 plus root 10 over 2i. Just arithmetic, man. You know what I mean? And that's no big deal. What do you guys think? This is where we're stopping today. Who's excited because they were like, this was some easy junk today that we did? Yeah. You ready to get less excited?
I like solid.
Yeah. Here's the good news, though. 1 through 40, yeah. But how long did these problems take that we did? These were like 1-minuters, right? They weren't bad. None of them are bad. You can knock this stuff out. We're stopping here, so you have like 40 minutes or whatever to bang this out. If you're, diligent, you might be able to finish the whole thing before we're out of class, which would be pretty righteous to finish the math homework for the day, especially since you have to worry about a math test coming up later. Maybe it just is nice to knock out most of that homework. You know what I mean, guys? I'm just trying to help you out a little bit. All right, I'm done talking.